Hello everyone, thank you for attending this session. My name is Shae Esmaeili and I'm from University of Florida. I'm going to present our paper, Detection of Scale-Hand Interactions in Virtual Reality regarding the effects of motion direction and task complexity. VR technologies have been around for decades in order to create simulated environments, and its applications have been used in different areas. For example, we have educational applications offering individual or collaborative learning experiences for students and teachers, entertainment-related applications like a variety of VR games, which are really common and popular. And we have training applications such as medical training or military training, and many, many more areas that VR can be found in. By tracking the head, hands, or even the entire body, users can interact with virtual environments using familiar movements and gestures. Often, as a goal is to make VR interactions more realistic and closer to the real world, as well as natural and intuitive for the users. Therefore, virtual movements are usually determined by a one-to-one mapping based on physical movements in the real world. This mapping will let users' interactions in virtual world being the same as real world. However, one-to-one mappings might not always be preferable or possible for all VR applications. For example, when we have a limited physical space, we are bound by these limitations and we are not able to explore fully in the virtual world. Or when we want to interact with distant objects in the virtual world, but we are limited by the actual reach distance in the real world. To address these problems, modified interaction techniques are sometimes used. For example, redirected walking techniques allow users to use their physical walking, but traverse virtual spaces that are larger than the physical space. Another technique regarding the head movement is amplified head rotation, in which smaller physical turns are mapped to a larger virtual turn, then allowing users to view the entire surrounding environment, but with small head movements. For hand movement, changing the scaling for hand movements can also be used to reach faraway objects, which has been introduced in the go-go technique. And these are just a few examples of interaction techniques. Regarding modified interaction techniques for hand movement, there are various methods such as go-go technique, body warping, word warping, and so on. In this paper, we focus on hand movements with gain-based warping. Gain-based warping scales the position of the virtual hand by a constant value along the displacement vector between the physical hand over the hand and the word origin. Therefore, by using this technique, we can make hand movements in virtual world faster or slower than the real hand movement. But how about the users? Do they still feel natural and normal with these modified interaction techniques? Or do they perceive the differences? And if yes, what are the effects on users' experience in virtual world? Since large deviations in interaction fidelity may potentially provide distractions or a loss in perceived realism for users. In order to address these questions, previous work has been done on estimating the detection thresholds using psychometric functions for some of the hand remapping techniques. But there is still little knowledge on detection thresholds for scaled hand movements or gain-based warping that we talked about, especially regarding different types of hand motion in VR and in different task complexity scenarios. So inspired by this motivation, we want to answer the following research questions. First, how do detection threshold estimations differ within each single degree of freedom for scaled hand motion? And second, how do detection threshold estimations change with respect to task complexity? Complex switching motions in cognitively demanding game scenarios with different levels of complexity. In order to answer our research questions, we conducted 2 psychophysical experiments to be able to measure user perception and to estimate the detection thresholds using psychometric function. In experiment 1, we only focused on simple hand movements and limiting the user to move their hand in only one direction at a time to answer our first research question. And in the second experiment, we focused on different levels of cognitively demanding scenarios in a game context to increase cognitive demands for users. In this experiment, we didn't limit the user hand movements and they could have moved their hand freely. In both experiments, we adopted a 2 alternative force choice method in which participants are exposed to different magnitudes of scaled hand movements in virtual reality while moving their hand and being asked to choose between normal and not normal based on the perception of the virtual hand movements. So let's start with experiment 1, simple hand movements. In this experiment, we had 2 independent variables. The first one, we had 29 different scale values, 14 in the range of 0.5 to 1, which were slower than normal hand movement. Then we had normal and also faster than normal. We had in the range of 1 to 2. And for the second independent variable, we have 3 directions, x, y, and z. X shows the horizontal plane, y is the vertical plane, and the z is the depth plane. In this experiment, we followed the within subjects study design with repeated measures. We had 46 university students as our participants. In this video, you can see the differences between slow and fast scale hand movements compared to the normal. At the top, you can see the slowest hand movement. In the virtual world, you can see that hand movement is much slower than the normal one. In the middle, you can see the normal hand movement, which is the one-to-one mapping between the physical hand and the real hand and the virtual hand. And in the bottom, you can see the fastest hand movement, which is in the real world. In the virtual world, this is like much faster than the normal world. Here you can see a demo of experiment 1, one setting. In this, you can see that the user is moving their hand in the X, now in the Z, and now in the Y direction. Each participant completed each direction one at a time with all the scale values, and the scale values were randomly ordered. We also counterbalanced the direction orders for each participant. For the results, because of our 2 alternative force-choice study approach, we conducted a psychometric data analysis. We logged the participants' answer to the normal or not normal question, and then we aggregated all the answers per each direction. We calculated the probability of normal answers divided by the total of normal and not normal responses. And then we fitted psychometric functions for slow scale hand movements that you can see in the left, and for the fast scale hand movements in the right. The drop-down lines present the detection thresholds based on a 50% detection probability, and error bar shows a 95% confidence interval. Then we compared the detection thresholds for each direction in order to see whether there is a significant difference or not. In this graph, the star represents a statistical significance, and we found that there is a statistical difference between all of the directions in both a slow scale hand movements and fast scale hand movements. As you can see in this graph, we have the highest, for the fastest scale values, we have the highest detection thresholds for for Y, and we have the lowest detection thresholds for the X that I'm going to talk about more in the discussion about this. So for experiment 2, task complexity in a game context, we have 3 independent variables. The first one is the same as experiment 1. We have 29 scale values for slow, normal, and fast. And we have 2 task complexity levels, a basic game and a complex game. Again, in this study, we followed a within subject study design with repeated measures, and we had 20 university students as our participants. In this video, you can see a demo of the basic game. In the basic game, the user can move their hand freely in order to catch some targets and get a score. And then they were asked whether was the hand movement normal or not normal. In the second version of the game, complex game, we try to increase the task complexity in order to be more cognitively demanding, and by adding an arithmetic equation that the user had to solve this equation, and then based on the color of the correct answer, they had to catch the correct target. The data analysis steps are the same as experiment 1. We logged the responses for normal and not normal for both of the experiments, and then we fitted psychometric function for slow scale values in the left and faster scale values in the right. And the drop-down lines present detection thresholds based on a 50% detection probability for complex version and the basic version. Then we compared the thresholds to see whether we find any significant difference or not. We only found significant difference in the slow scale values, but for the faster scale values, we didn't find any significant difference. In this slide, you can see a summary of our results. We present the range of scales that can be applied to the motion of virtual hand, while the difference between the physical hand movement and the virtual one is unnoticeable to the users. We estimate detection thresholds for each of the direction, as well as compound hand movements in the complex game scenario. These values are estimations of detection threshold that can be applied to either increase or decrease the speed of the virtual hand. So what are the implications of these results? So we found that hand direction matters. Our results provide new insights on human perception of scaled hand movements in different motion direction in virtual reality. We detected significant difference between detection thresholds in different directions, both for slow and fast scale. As you can see, the range was narrower for the detection of modified motion scaling in the horizontal plane. This may be due to the visual field of view of horizontal plane covering a larger range than the vertical. Our interviews of participants also said that people are more familiar with hand motions in the horizontal plane, and therefore it can detect the abnormality better. Many common object motions make use of horizontal and depth motions. For example, when we want to move objects on a table or desk, or when we want to open the door or reach for objects. On the other hand, for the Y direction, you can see that our results show that we can have the highest range of detection thresholds, and this is probably due to the more limited degrees of field of view in the vertical plane. Additionally, during the interview section, our participants reported less use of vertical motion in day-to-day interactions, which may be related to a larger range in detection thresholds for scaled vertical hand movements. Overall, the contributed knowledge of detection threshold for different directions is relevant when considering applications of scaled or remapped hand movements in VR applications. For example, in applications that require use of vertical motions, for example, lifting the objects or making climbing gestures, hand movements can be scaled higher using the estimation detection thresholds, and therefore provide higher reach for users while preserving their realism. Similarly, estimation of detection thresholds for depth interactions can be useful in applications with back and forehand movements, for example, reaching for virtual objects or opening or closing actions. Moreover, these scale ranges are valuable for the design of future VR applications that use scaled hand movements as a modified interaction technique while aiming to provide a realistic, natural, and immersive experience for users in VR. Slow scale hand movements can be beneficial in situations where accuracy of an interactions in VR is important. For example, using VR for hand rehabilitation training or medical training. Therefore, they can be used in such applications to provide more controlled environments. By applying scales within the proposed threshold, it can be expected that discrepancies between VR and real world would not distract users. On the other hand, faster scale hand movements can be useful in VR applications, aiming to provide a higher range of hand reach or faster hand interactions, for example, in VR game applications. And VR users can move their physical hands less, while their virtual hands are moving faster and can be used to reach far distant objects. For future work, we found no significant results between the basic and complex versions of our tested game scenarios, which can be attributed to our study design limitation, but it may be that the detection ability is not greatly affected by cognitive load differences, as previous work also did not find any significant difference. Also, we can also test for detection thresholds for different hand remapping techniques, because we still have no knowledge about other remapping techniques. Thank you very much for your attention. This concludes my presentation. Please feel free to check out our paper, and I will be here and also in the Slack to answer any of your questions. Thank you.